talk in this session by Yuzhou Chen, and he will discuss assessing urban form and climate justice with deep learning. The floor is yours.
Okay, thank you much, Julia, and good afternoon and good evening, everyone. And so, first of all, thanks very much for inviting me for such excellent the TELS, the annual meeting conference, and I'm very honored to present my work here. And so today I will present our recent project. So that is the assessing the urban form and the climate justice with the deep learning. And this is the joint work collaborated with the City of Hope and NASA JPL, University of Texas at Dallas, University of California, San Diego, and Temple University. Okay, so first is motivation. So as we know, our planet's climate continues to change, right? So from the historical to the current to the future patterns, and actually the cities determine where the most devastating effects of the, for example, like the air pollution and the heat islands. For example, like the higher the daytime temperatures or the reduced the nighttime cooling, so will be felt. But however, these effects actually will not impact the urban dwellers equally. So for example, the urban form is underlining the drivers of the structures resident through the landscape heterogeneity, okay, and the structural inequality and the infrastructure disparity. So around the global, and the research find that the minority and the marginalized communities actually they experience a greater exposure to the ambient and the point source air pollution and like the hazardous risk. For example, like the higher urban temperatures, and also there are many findings found that this disparity actually happened in the marginalized communities in the U.S. Okay, and like the air pollution and the heat islands operate actually in a very different way to impact the health of the individuals, especially in the marginalized communities. So who experience the great exposure. So that will be the short-term and long-term health outcomes. For example, like infectious disease and so on. Okay, and so in order to reduce the previous mentioned the environmental risk impacts, especially for the urban population. So here we proposed a urban form, the environmental risk and the structural resilience project workflow. So from as shown in the figure 1, we can see that actually the NASA satellite image dataset play a key roles in this workflow, and as such, we propose the multiple deep learning models and utilize these models to enhance the visibility and the utilizations of the NASA satellite image datasets. So in the context of the environmental and the climate justice. Okay, and more specifically, here I would like to introduce more details of this workflow. So so in the initial stage, we will collect the images, so that is a NASA satellite image library, right? And then we fill it into our proposed deep learning models. And here we give the 3 options from the convolutional neural networks to the geometric deep learning to the recurrent neural networks. Okay, and for the convolutional networks, as we know in recent years, it very achieves many promising results, not only in the computer vision but also in the graph mining and graph representation learning and the natural language processing. And so about the convolutional neural network science, so the convolution layer with the small receptive field, so it can help us to capture the local neighborhood pixel information and features, right? And the convolution layer with the large receptive field, somehow it can help us to learn the spatial contextual features. Okay, and about the geometric deep learning, so actually it is tend to generalize the deep neural networks to the non-Euclidean domain, for example, like the graphs and manifolders. And one of the popular geometric deep learning model in recent years appeared is the graph neural network GNNs, and most of the GNNs, their core idea is the iterative massive passing scheme. So that is, these schemes allow the framework to collect the information. Okay, so for from the neighborhood information, so for each target node. So finally, we can obtain a latent node level embeddings, so which can help us to better understand the complex relationships between the nodes, and also better to explore the complex structures in the graph. Okay. And the last one is the recurrent neural networks RNNs. So that is the deep learning framework. So can help us to capture some dynamic temporal patterns or behaviors. And since we would like we would like to extend and apply our proposed model to the tensor images or tensor graphs. So in this case, we can combine either the CNN or the deep learning, geometric deep learning models with the recurrent neural networks based model, and to capture both the inter and the intradependency among the different timestamps. Okay, and the outputs of these deep learning models, this block will be fed into any the unsupervised learning algorithm, for example, like the k-means, so that can help us to cluster the features we obtained, right? So for example, we can get the latent, the urban feature clusters, and these results can also will be very useful for the environmental risk prediction and also the community collaboration to reduce the hazardous risk. Okay, and so as mentioned before, so in order to to mitigate the hazardous risk, the environmental risk, especially in the most vulnerable, the urban population. So here we stress the 3 points for the policy makers. The first is to increase the clarity into these relationships between for example, the urban features, the structural resistance, and the hazardous risk, and so try to clarify these relationships, both present and historical. And the second is to develop, to propose, or to utilize some metrics so that it can account for the complexity of the urban change in relation to the structural resistance practice, so that can place the population at the heightened risk from the air pollution and the heat accident effects. Okay, and lastly is to propose the methodology or the model architecture, so with the ability to identify the intervention points to mitigate this environmental vulnerability. Okay, and here the figure 2 here shows the above mentioned the patterns in the Los Angeles and San Diego, and the top is for the Los Angeles and the bottom is for San Diego, and we can find that in the LA, that for the PM 2.5 in LA, we can see there are the pockets of the very high exposures, so that directly line up with the historical right-lined community, right, near the Santa Monica here, and the Hawthorne and the central LA, right? And the subfigure on the right side here displays the current data isolation of the African Americans in this region. Okay, and also we can find similarly the similar patterns appear in the Hawthorne and the Santa Monica, and also in the central LA. Okay, and in the San Diego, we can see the relatively the higher the heat being experienced in the red and orange line data neighborhoods, and so which is categorized as hazardous the area to land in the historical. Okay, and also we can find there are some line data with the green and the yellow color, so that is neighbors. Okay, and on the right side we can find the Hispanic this isolation tend to align with the higher heat pockets in the community, and especially in the El Cajon and the central San Diego. Okay, and so next I will introduce the data set we used in our experiments. So that is the satellite imaginary product from the NASA satellite. So all the imaginary products will be used as the level 1 also rectified and geolocated radiance or the backscatter data set. Okay, and more specifically, the MODIS aboard this the terrain, the satellite has the 38 spectrum bands, and 2 out of these 38 bands will be used when evaluating the performance of the feature extraction, okay, at the 250 minutes, and 5 out of these 38 spectrum bands will be used to evaluate the performance of the feature extraction at the 500 meters, okay, and moreover, we consider the 2 data sets. First is the 2 data sets from this the satellite imagery. One is the ETM plus aboard the Landsat 7 and also the OLI on the Landsat 8. So in this presentation, I will show results on the Landsat 7. So which they have the 6 bands at the 30 minutes the resolution, and another has the 50 minutes the panchromatic the band. Okay. And 2 instruments are used to collect this data imagery. So the first is the multispectral medium resolution scanner, okay, and the second is the high resolution technological camera. Okay, here is the visualization of some of the data set and the satellite image we used in the experiment, and we can see here is this is the San Diego, the county, the boundary, so which is colored in the blue, right? And as we mentioned before, we only focused on the urban area, so which is colored in the purple, okay? And here is some the satellite images from this urban area. Okay, so next, I will introduce how we modeling the satellite images, for example. And one important thing I would like to highlight here is actually we convert the satellite image into the graph. And here I will give a very basic introduction of the graph representation of the satellite image. So the first of all is why we consider the graph, since the actually graph-based representation can be used to model in a variety of problems and domains. And moreover, the graph-based representation, actually they can have several multi-resolution representation of the same object. So for example, like the pixel level and the superpixel level representations, so they can be, often they can be modeled by using the graphs. Okay, and furthermore, about the superpixel-based the representation is it can somehow not only reduce the input image size, so that makes the whole model more efficiently, but also it can help us to capture the valuable topological and high-order structural information from complex. So that is the information we cannot detect from the traditional convolutional operation. Okay, and so that is why we consider using the graph representation instead of directly apply the model on the images. And next, I will introduce how we convert this image to the graph. So we will apply the simple linear iterative casting SLIC is a function on the target image. Okay, so and here the H is the height, width, and W is the width, and the K is the number of channels. Okay, and in our data set, we consider the 3 channels. And then through defining the predefined the number of superpixels, so we can get the corresponding the superpixel matrix S. Okay, and after that we can obtain a region adjacency graph RAG. So where the detailed algorithm showed here. And so in this case, we can treat each superpixel as the node or the vertex, right? And then we can add in the edges, so that is connect the superpixels. So if they are in the neighbors, okay. So here is the very tall example about how we convert the image representation to the graph representation. So here you can see there is a beam that it's bloom in the flower, right? And so first we apply the SLIC this function on this image, and we can see that each cell or this small box represents the superpixels, and we can find actually these algorithms treat the head of the beam as one cell. So that means the function think the pixel information in this area, they should be the same. So they can be used the one pixel to represent the subpixels. Okay. And then for each cell, we pick up the center point as a node, and then we can see here we connect the adjacent superpixels, right? Then we can get the corresponding graph representation. And here is more the visualization on our used the satellite images. And figure 3 here shows the image with the superpixel segmentation by setting the different number of the superpixels. So the left side here, the subfigure is if we set the predefined superpixel number equals to 50, and the center is 100, and the right side is 200. Okay, and the figure 4 here shows the procedure of how we convert the satellite image into the graph representation. Okay, so A is actually one toy example of the satellite image, and by using the SLIC function, so we can get the segmented labels, which is shown in the image, right? And then we will connect the adjacent superpixels, and finally we can get the corresponding graph representation. Okay, and so now we have the satellite images, and also by using the SLIC functions, so we can get the corresponding the satellite superpixel graphs. Okay, so next let's discuss about the deep learning models we used in the experiment. So first is the convolutional network CNNs. And so in our study, we consider one very representative convolutional network, so that is the ResNet residual network, ResNet, which is proposed by the Kaiming He in the 2016. So the main idea of the ResNet is it adds us skip connections in the neural network architecture. So in this case, it can solve the vanishing and the exploding gradient problems in the neural network architectures, especially for the architecture with deeper layers, say up to 100 or 1,000 layers. Okay, and another point I would like to highlight here is why we consider ResNet, since ResNet can help us to capture and learn the residual representation of the image instead of the signal representation directly. So which actually is aligned with our goal to capture the urban form. Okay, and in the practice, we start from the pre-trained the ResNet model with 152 layers as the baseline. So to compare with the outcome of the results from the geometric learning models, which I will mention later. And figure 5 here shows the overall architecture of the ResNet with the 152 layers. Okay, and so this predefined the ResNet with 152 layers model can actually in the beginning is defined to classify the images into 1,000 classes. Okay, and so which is how we train this ResNet model. And so therefore, in this case, we can extract the output vectors from the final layer prior to the fully connected layer. And this modification somehow can help us to obtain an image representation with the 2048 dimensions. So that is for each examined images. Okay, and these images can be definitely used as the extracted feature outcome. So from the CNN-based model, since finally we will use this safely the extracted feature outcomes and feed it into the the unsupervised learning algorithms, and it can help us to cluster these images. And figure 7 here shows the one example of the input images being processed through the layers of the ResNet, and we show the output every 5th convolution layer in the model. Okay, so next I will discuss and introduce the model, another deep learning model we use in our experiments, that is the graph neural networks. And there are two reasons why we consider GNN is the first of all is about the CNN. Somehow it can hard to capture the long range dependency in the image. And another point is the CNN-based model always missed the geometric context information. But however, for the GNN, it will be very easy for the GNN model to encode this kind of the geometric context information. So, but which is very hard to be inferred from the 2D or 3D images by using the CNN. Okay, and we address these issues by proposing superpixel, the simplicial graph networks, where the superpixel means our model will be applied on the superpixel graphs. And about the simplicial complex, actually it is the higher order structures, and the definition of the simplicial complex actually is the collection of the finite set, so closed under taking the subset. Okay, and in the graph we think the zero simplex as a node, and one simplex as the edge, and two simplex as a field triangle, and three simplex as a tetrahedron, and so on. Okay, and then another thing we'd like to highlight here is we don't utilize the traditional the graph neural network framework to learn the features in the superpixel graphs. So here is the toy example about the vanilla graph convolution. So we can say if we want to obtain the latent node representation for target node A, somehow we can only collect the information from its one-hop neighbors. So that is the B, C, D nodes, right? But it may miss some higher order structures. So in this case, that is why we consider the superpixel graph networks. Okay, so in this case, suppose we have the target nodes. By using our proposed framework, so we can say, right, for target node, this black node, we can collect the information from its first one-hop neighbors, 3 nodes, and also we can extract the information stored in the edge connected with this black node, right? And moreover, for the edge, somehow it can be updated. Its information can be updated through its adjacent, the edges, and also the triangles which involve this edge. So that means compared with the GNN, our simplicial graph convolutional network can fully utilize all the information in the graph. So that will be so that will be very important and will be very important for the applications. So that needs is relevant the connectivity information.
Yuzhou, time. I just want to remind about time.
Sure. Okay, thank you. Yeah, so, okay, and here is the approach of the flow chart of our GNN model. So, yeah, I will quickly go through it. So, firstly, we convert the image to the superpixel graphs, and then we apply the simple graph convolution on the superpixel graph. We can get the corresponding simple complex level embeddings, and also we use the global pooling layer to get the graph level features. Okay, and then we feed them into the MLPs to progressively learn a hierarchy of the images from the local and global point of views. And finally, we for the unsupervised learning, so we consider using the mutual information maximization, so between the graph level representation and the simplicial complex level representation. Okay, so here are some class results, but let me directly show the numerical results. So here is a comparison between our proposed L2 GNN model and the CNN model. And also we consider 3 evaluation metrics. So that is silhouette coefficient, the Klansky, the Harabas, the index, and Davis boarding the score. Okay, and also we consider 4 clusters from 10 to 40. And as we know, for silhouette score and the Klansky, the Harabas index, the higher the better. So you can see our proposed L2 GNN model can always highly significant outperforms the ResNet with the 152 layers. And about the Davis Bodling score, the lower the better. So we can find our performance is also the higher performance than the ResNet model. Okay, so here are some conclusion and future work. So to our best knowledge, the proposed the S2Gen model is the first work to consider using the simple complex representation framework and the graph learning this framework for the unsupervised satellite image learning. And from the extensive experiments results, we found our proposed model can always outperform the representative based model, so that is a ResNet model. And in the future, we definitely would like to extend our existing architecture and framework to the time series images. And moreover, we would like to study the spatial and temporal features beyond the San Diego counties, right? And also we would like to extend our proposed algorithms to the COVID-19 pandemic, is the spreading analysis. Okay, thank you much. And any questions?
Thank you so much, Yuzhou, for this very complete presentation. I think we have time for one quick question. If somebody in the audience have a question, you may also write it down and we can. Okay, if nobody asks a question, Let me start. You're using satellite datasets, right? So it means that from satellites we have multi-channel information. So which one of these channels are you using in your datasets?
Yeah,
why?
Yeah, we use the red, blue, and the green channel. So the RGB channels, so only 3 channels.
Okay, that leads me to the next question. Why RGB? Why, I mean, do the space of color actually have an impact on the results? Because you could use HSB or any other thing.
Yeah, that's a very good question. So in the practice, actually, when we contract the superpixel graph, so we will reuse the features in the different channel. So in this case, the final node feature matrix will be the n by the 5, where the 5 is, so the 3, where the 5 is 3 plus 2, the 3 is from 3 channels, right? And the 2 is we do the average and the summation of these 3 channels. So in this case, although we use the graph representation, but we still can, keep and fully utilize this channel information, and we can represent in the node feature matrix. Okay, got it. So you didn't try any other color space? We only have 3 color space, but yeah, I think I know that some images may have the multiple 100 channels. Yeah, but we don't have this kind of data set yet, but probably in the future it will be a challenge. Yeah. Yeah, thank you. Any last question? Okay, if not, thank you so much for this session. This was a very interesting session on climate justice, data science perspective. Thank you to all the speakers, and I will leave the floor now to Claire, used to close the TIES annual meeting.